In this CSE 373 review video, we're going to be going over code modeling and doing a few practice questions. First, we start with the code that we're going to model. Then, we calculate a runtime function for that code, and after that, we use our big O analysis tools to come up with an order for that function. To recap how we calculate the runtime function, here's a simple example. We start by assigning a number of calculations to each line. And then from there, we have to identify that there's a for loop here, and this loop executes the code within it n times. So with that, we can construct our runtime function. And if you're unclear about how we get here, let me switch over to my pen, and you can see that this code executes exactly once and totals to be 4 calculations. This code executes n times and totals to be 3. So we have 3 times n plus 4. And then we can use our big O analysis tools to find out that this runtime function is in the order of O of n, as n is the dominating term. One important thing to note is that constant factors do not need to be exact for asymptotic analysis. So for the rest of the slides, I'm just going to be doing a +1 for each line instead of worrying about it, whether it's a +2 or a +3. We're going to be going over the Section 2 handout, problems 4C, D, and E. So let's start with 4C. Just like in the simple example, we're going to start by assigning calculations to the top 2 lines here that execute exactly once. Then we notice that this for loop goes from 0 to n, so the code inside of it executes n times. And we can assign our calculations for these lines as well. And in this for loop, we have another for loop where the code within it executes n times as well. So now we have to construct the function. So how do we do this? So these 2 lines we know will execute only once, so we add a constant +2 to our function. Next, we know that the code within this for loop is going to execute n times, so let's add an n here, and then whatever's in these parentheses is going to be whatever's in this block of code in the for loop. So this line will execute every single time we go into the loop, so we're going to add a 1 here. However, because we have a conditional, this line will not execute every time we go into the loop, and it'll actually only execute 1/5 of the time because it only goes into this if statement if I mod 5 is 0, so every 5th number. So we're actually going to add 1/5 of a calculation. Next, we go into this for loop. So everything within this for loop goes n times. We're going to add another n with another parentheses. And there's only 2 calculations here, so we can just do 2 and then close it off. But because this block of code is also in this if statement, this will be over 5 as well. So let's simplify our equation. So we get n plus n over 5 plus 2n over 5, and then plus 2 at the end. And then we can combine these terms and get 6n over 5 plus, oh, my mistake, this should be 2n squared. There we go. Plus 2n squared over 5 plus 2. And that's how we solve that problem. And we see here that n squared is the dominating term, so we know that in the worst case, the tight big O bound for this code is O of n squared. Next, we're going to go over 4D. So for this problem, I'm actually not going to go through and assign all the +1s. I think at this point we understand how to do that, so I'm really just going to focus on the n terms or larger and not worry about the constant factors. But there will be some +c or plus constant factor added to this runtime equation. So we see here that there's a for loop that goes n times, so all of this code is going to be executing n times. Now we have another conditional here that says if n is less than 100,000, execute this code, and if it's not, just add +1 to x. And if we do go into this top conditional, we're going to be executing another loop that goes over n times. So this line of code gets executed n times, but only for the first 100,000 values of n. It might seem like because this number is so high, we're going to be doing n times n work, but this is actually not true because as n goes to infinity, all values from above 100,000 to infinity are going to go into this other conditional, and that's many more than 100,000. So as n goes to infinity, it's actually going to only be doing work on a order of n. One really important thing to note, and I'm going to be going over some examples, is best versus worst case is not the same as O versus omega. So for this example, there's a method called print pairs, which takes a list of integers, and for every integer in that list, prints out every possible pair. So I think it's pretty clear that this code will be O of n squared, because there's two nested for loops that both go to n. However, there are also no cases. No matter what the contents of our list are, as the list grows infinitely large, the runtime will always be O of n squared. There's no way to get better or worse runtime. So here's our runtime equation, as we can see that it's some constant times n squared plus some constant times n plus some constant. So the dominating term is n squared, and we have O of n squared and big omega of n squared. So the tight big O is n squared, and the tight big omega is also n squared. And because of that, we have a big theta of n squared. This is code with a simple polynomial runtime function, and for simple polynomials, you will never have a different big O and big omega, and your big theta will always be the same as those two. The key here is that the state of the input, the list, has no effect on the runtime. As the list grows infinitely large, which is what we care about, the content of the list has no effect on the runtime of the code. Here we have an example where there are cases in our code that both lead to simple polynomial runtimes. So this is very similar to the other piece of code in the last example. The only difference here is this if statement that only does this extra n bit of work if the element of the list is odd. So here we have best and worst cases that depend on the content of our list. The best case here is that all the elements in our list are even, and we will never go into this if statement, and we will never execute this n amount of code. Our worst case is that all the elements are odd, and we do these doubly nested for loops every single time for every single element of the list. So here are our runtime functions for each of these cases. For the best case, we have some constant times n plus some constant, which is going to be on the order of n. And for the worst case, we have some constant times n squared plus n plus some constant, and that's going to be on the order of n squared. So here we have two big thetas, so two functions depending on our case, each with their own big O and big omega, which are the same for each case. And the key here is that the state of our list, the state of the input, has effects on the runtime. So depending on how many odds and evens there are, the runtime will be better or worse. For each case, however, this has no effect on the big O upper bound and the big omega lower bound. For each case, we have our own set of big O and big omega. Our final example here is a divergent function that calculates whether a number is prime or not. And the most important thing to note here is that there are no cases. So maybe for each individual n, this code will perform better or worse. However, as n grows infinitely large, the state of our input here does not have any effect on the runtime. We have numbers from 0 to infinity, and the runtime for each n will be what it is. So there are no cases here. However, the tight big O and the tight big omega are actually not on the same order, because if it's a prime number, our loop will go all the way up to our n. If it's not, our loop will stop iterating after only a handful of iterations. So for this piece of code, we actually don't have a big theta that exists. This is displayed visually here. As we see, as n goes to infinity, we have values of n that are prime that take n computations. So that's our tight big O of n. But for a lot of values of n, we have computations on the order of 1, constant time. Because of this, we have 2 different bounds, and our big theta doesn't exist. Okay, that's going to be it for this review video. If you have any questions, feel free to post on Piazza or come to office hours. Make sure to like, comment, and subscribe because TAs actually only get paid in YouTube AdSense money. So we are actually desperately counting on your views. Thank you.